Okay, so the second installment of my series of sigma model and quotient discussion starts now. And before I start for real, I want to say that the main body of the things that I'll be reporting on has been derived, as far as I'm concerned, and involved in collaboration with Chris Hull, Martin Rocek, and Nigel Hitchin mainly. So I gave some references to that. Let me remind you what we're trying to do. We're looking at sigma models, and we saw that sigma models define a geometry on the target space. And if the sigma model has so there's a metric, so if the sigma model has an isometry, we can gauge that isometry and then reduce the sigma model to another one on the quotient space, that is on the space of orbits of that isometry. And that was all very clear and quickly done in the bosonic case. But our real interest is in the supersymmetric case, because then we have more interesting target space geometries. And the difficulties that we encounter then are that we need to discuss isometries in the case of supersymmetric sigma models, and that discussion gets more and more complicated depending on how many supersymmetries we have. But once we have that, we have geometries on the target space available that are if we're in 2 dimensions in the 2,2 case, they're Kähler, and the 4,4 is they're Hyperkähler. So by constructing a sigma model with that symmetry, we construct that kind of geometry, that kind of complex geometry on the target space. So let me just, and the target space geometries which are of interest are the Kähler and Hyperkähler. And I will start by discussing complex geometry a little bit. Then I will gradually show you how the gauging of those sigma models how that goes in the 1,1 case, and etc. And we'll end up with a gauging of isometries in a 4,4 sigma model, and that target space is Hyperkähler. And that's very good, because then we can start from a simple Hyperkähler with isometries, and gauge the isometries, and then go to the quotient space, and that will give us a new Hyperkähler. And this is a method which in fact gives us globally defined new geometries. And it's a method that it is completely based in the high energy understanding of sigma models. Okay, so let me start by saying something about the geometries. So, starting by Kähler geometry, what we have is we have a manifold and a complex structure and a metric. And that this is a complex structure means that it's an endomorphism of the tangent space that squares to -1, and that it is in fact integrable. This doesn't make it integrable, but if we have a certain tensor, the Nijenhuis tensor equals 0, then it's integrable, and we call it a complex structure. And we also have a relation to the metric. So we have that this has to be fulfilled. So this is her hermeticity condition of the metric G with respect to the complex structure. And once we have that, we can introduce a two form, which is we write as G times J. So I'm suppressing indices here, but this is a two form. This lowers one of the indices here. This is a mixed tensor, and this lowers one of the indices. Okay, and when it's scalar, we also have that this is that it's globally defined, and that the exterior D vanishes. So it gives us a symplectic structure on the manifold.
Remind me, we know that omega is antisymmetric because?
That's here.
It's in there.
So you move this to the other side, you get a minus sign, and that's exactly yeah. And what else can I say? There's also the covariant derivative of J is 0, where this is the covariant derivative with respect to the Levi-Civita connection for this G. Okay, right, so we can also go to canonical coordinates. By canonical coordinates, I mean coordinates where J is I times 1, 0, 0, minus I times 1. And there one can derive the fact that the metric has potential. So if we call these zeta and zeta bar, then the metric has only components which are which are d squared k dz bar. So there's a potential for the metric, and this whole story is defines the Kähler geometry. In fact, it's a little bit what can I call it? Over-constrained? No, it's not over-constrained, but not all of these are independent. These two you can play with. But this is a good way of thinking about the Kähler geometry. But as I said from the outset, we're actually interested in Hyperkähler. And a Hyperkähler is something, geometry, which is more constrained than this, in that there are a whole set of complex structures, so Ji squares to minus 1, and also etc. And the metric is in fact Hermitian with respect to all of these. And the Nijenhuis tensor vanishes, etc. So for each I, we have this set of relations, but we have more. I'll just write the definition of more here, which is that we have the algebra of the quaternions satisfied. So this is minus delta ij plus epsilon ij k j k summed over k. So I is 1, 2, 3. Forgot to say that. So there are 3 extra. There's also the ordinary complex conjugation. So there's actually 4 complex structures here, but these 3 satisfy this. And in fact, So this is the algebra of the quaternions, and in fact, you can also say that you can define a new complex structure, J1 plus BJ2 plus CJ3. This is again a complex structure, provided that we're on the unit sphere. Okay. So as you see, this is a very intricate set of relations, and a very interesting complex geometry.
Can I ask a question? What's the equivalent of the Nehenhausen condition for the Hyperkähler case?
Sorry, what?
What's the equivalent of the Nehenhausen condition for the Hyperkähler case?
Oh, there's one for each j. So okay. So we define pi I is equal to 1/2 1 plus I j I. Okay, and then you ask for that the tangent space, you can define subspaces of the tangent space that are involutive with respect to this for all I.
And those all three, so that's three conditions that are required. All three of the complex structures have to have a vanishing Nehenhausen tensor.
Yeah. Yeah.
Okay.
But you cannot define coordinates where they're all canonical. You can at any given situation you can define one set of coordinates that are canonical for one of the j's, and the other ones will be related by non-holomorphic transformations.
So is all the three conditions independent with each other?
These are, yeah. I don't know which three, if you mean these three.
The vanishing of the...
Oh, these here. These are not all independent.
No, but I think amongst the eyes is the question, right?
Sorry?
Can you have partially complex, partially almost complex?
Oh, well, that's equivalent to asking, I think, can you have n is 3 supersymmetric? Yeah. And I think you can, but that's not relevant for the thing that we discussed now. Okay, so there's some more interesting relations that to do with the holonomy of the various geometries. I don't think I'm going to use that, so let me just say that the Kähler geometry has a unitary holonomy group, and Calabi-Yau then has a special SU holonomy, and finally Hyperkähler has SP holonomy, and that's not saying very much. I also have to define what's the dimension and so on of the various geometries or manifolds, but just to indicate that there is a relation to that.
If 3 is not automatically equal to 4 in this case?
Well, that's the question. I mean, if you do 3, 3, yeah.
It has to do with CPT.
Yeah. But I think I'm not saying. I think you can construct example where this is. It depends also on the dimension of the manifold you start from. Okay.
I mean, I think locally, as far as all those complex structures, you've got 2, then you've got a third one. But I think the integrability question is interesting. I think you could imagine having a Kähler manifold of dimension 4 times something, where you could define some extra, almost complex structures which weren't necessarily integrable.
Yeah. Yes. But I think that was the question, wasn't it?
Yeah. So I think you can have things which look as if they've got a Hyperkähler structure locally, but they're not all integrable.
That's-
1 equals 2.
Yeah, I agree. But the case that we'll be interested in is this, where you have three complex structures, not almost complex structures. Okay, so this then is the kind of tangent-space geometry we come across when we write down sigma models. This one for in 2 dimensions, this one for a 2,2, and this for a 4,4. And we then have to discuss, if you remember, we introduced isometries, so we have to see if you can do a reduction or a quotient with isometries in the supersymmetric case. So go back to sigma models. So if we start from the n is 1, so we have an action, which is this. It's a d minus phi nu. Okay, so where this is in n is 1, I've now gone down to or up. I was talking about 2 dimensions before, but to have less to write, I've now gone to 3 dimensions. But the phi's are still chiral. And this is the n is 1 measure. Okay, so this is your n is 1 sigma model in 3 dimensions, as it happens, and you assume that there is an isometry, and then you gauge that isometry as we did in 2 dimensions. So this goes into integral d3x, and then the measure is still the same, but you have a covariant d. Where d plus minus on phi, as I emphasize this here, the construction is completely analogous to the bosonic case. So we just introduce a potential, a connection, d plus minus phi mu minus a plus minus b k b mu of phi. So these are the k's are the generators of a possibly non-abelian algebra, and they're the generators of the isometries of this metric. We introduce that, and then we integrate out. Oh, that's a bad wording. That's bad wording to say that you integrate it. What you do is you extremize this action with respect to A and find one particular connection A, which extremizes this action, and then you plug that one back into the action, and you have something which is still gauge invariant in that. It's still a gauge connection in that sense, but it also reduces to a theory or a model on the space of orbits. which leads to, so plugging it back leads to the following. Oh, I'm not going to fit this. It's this times d minus phi mu. Okay, so this is the metric on the quotient space which is completely identical to the one we found in the bosonic case. So here H A B is defined to be K mu A G mu nu K nu B. And this with upper indices is the inverse. Okay, so maybe I should write that. H A B H B C is delta A C. Okay, and what's more, you also see that you see that it's identical in construction to the bosonic case, and you also see that supersymmetry is preserved because it's all written in terms of n is 1 superfields and covariant derivatives. So no problem to do the reduction for an n is 1 sigma model. But on the other hand, an n is 2 sigma model has that's where we start running into intricacies. So I write the n is 2 covariant derivatives as blackboard bold, and so we have an action which is this, and then we have the potential phi bar. So this is my sigma n is 2 sigma model. And now we want an isometry, and we're going to call it x actually, but we want xk to be 0. If we have xk is 0, that guarantees that x generates an isometry, that x is an isometry. But it's not the full story, right? Because you can, as we talked about, you can add to k a so-called Kähler-Gauge transformation. So more generally, we can have this. xk is, I'm using notation which I've taken from one of the papers. That's this notation. So this is a Kähler-Gauge transformation, which means that it's a sum of a holomorphic and an anti-holomorphic function. And if you plug that into here, because the plus minus on phi bar is 0, this one is gonna vanish. So what we're saying is that this is not the most general case. The most general case is when this is a Kähler-Gauge transformation. Then, of course, the action here will be invariant because these two functions will be annihilated by the measure here.
You just remember in the n equals 1 case, the three-dimensional spinors are basically Majorana, is that right?
They're basically the same as in 2 dimensions. So
Well, in 2 dimensions you can split them into one component things.
you can't in 3, but you have the symmetric part as well when you go to vectors. But I don't remember exactly.
So you're not adding a complex conjugate in n equals 1. It's already real by itself. Is that right?
I think you're right. I think I should have a d bar here actually.
Well, that was what I was worried about.
Yeah, I think I'm sorry. I think you're right. So it's a d, and so you generate both a and a bar. I think that's the case.
No, 3 dimensions. The spinors are real. Am I right?
They're Majorana, so it's not a d bar. Okay.
Yeah. So spin 2-1 is SL2R. So you've got 2.
Yeah. That's right.
In n equals 2, you're making them complex.
That's right. And right now I'm confused about the two, but this is right now. Okay. So if you were to reduce this to 1,1 or to 1 in this case, you would have both the complex and the complex bar. So it's going to look like this, but with bars on one of them. Okay, so that's the situation for n is 2. And what are we doing now? Okay, we want to discuss holomorphic isometries. Oops. And that means that we say that x will be xa, where a is the same index as here. So that's if we have that's what's it called? Not group indices, Lie algebra index. So it's this times this So this is in holomorphic coordinates. So here the coordinates are phi and phi bar. That's a special choice, but that's the choice which is very natural when we write down the sigma model like that. Okay, and what I should say is that this possibility for the 2,2 means that for the gauging of isometry for isometries for the Kähler case, which is this one, gets more complicated. And what I'll try to do now is to indicate what the complications are and how they're resolved. Okay, so we have this, and we have we start from the Kähler case. So we have a Kähler. This is Kähler, and it means that we have, as I said over here, a J, etc., and an omega. And you know, this J. So whoops, I haven't quite done it yet, but I'm sure I'm going to trip over this. So what we have is a Lie derivative along this isometry of J is 0, and the Lie derivative of omega is 0. This is what we need for isometries in this case. And so you know the omega is formed from the metric and G, and the metric G and J. Okay, and what this means is we have a situation where we have a symplectic form that's preserved by this isometry, which is a vector like that, and it means that we can write down a relation which is that Ix on omega is equal to d mu x. So here I have to explain. This is what you get. You know, this is you're familiar with this from Hamiltonian mechanics, and this is like a Hamiltonian, and this x is the vector field generated by a symmetry of the by a Lie algebra element that you can that acts on the manifold. So this relation is important, and that's the relation we're going to explore. And in the context that we're looking at now, this mu has different names. It is called the killing potential, which we'll see in a moment why. And it's also, mu itself is a moment map. So you can. So I should write this: mu x is x a mu a, and this is a basis for the dual Lie algebra. And then you see that mu becomes a map from the manifold M into the dual Lie algebra. And when you think about it like that, it's called a moment map. But I also called it a killing potential, and we'll see why that is now. Okay.
Is mu defined globally? Sorry? Is mu a local or global object?
Good question.
Because if it just comes from the vanishing of the lead.
No. They didn't. No, that's the point. That's the point. We're requiring it to be globally defined. Otherwise, as you say, it would just locally. You can always do this.
Okay.
Okay. So we're going to write this. Let's write this out in the coordinates where we have the metric look like this. I can't read this myself. This is a K, a potential. So if we do that, we have the following I X A K A P acting with P Q bar. So these are derivatives with respect to phi P and the phi bar Q bar of the potential K. Okay, so then I use that, and I then use this form of the metric, and finally I also use the fact that in these coordinates the complex structure has this form. So this is in fact what gives me the I here, which comes from this being the lowering the one index of the complex structure with the metric. So it's this, which is equal to this. So this is equal to d by d phi q bar on mu x. And here I haven't written out the dependence on various things on the coordinates, but that I should have done that, because this depends on phi. If we go somewhere, we can see that. Yeah, so this is k, is a function of phi. This one, the potential is of course a function of phi and phi bar, and so is the moment map. These are constants, okay? So when you see the arguments like this, you realize that you can integrate this. Both sides are derivatives with respect to q bar, so we can integrate that and find that so that's this guy, and now we just have the derivative with respect to the phi p, and this is equal to minus I mu x of phi bar. This I also write phi bar to be explicit, and that just comes from integrating this relation. But of course, it was a derivative with respect to phi bar, so we can add any function of phi, and in fact what we add is this function of phi, the one that we've previously, that notation is used here for the Kähler gauge transformation, and that's how it's going to enter the story as well. Okay, so what we finally find is we take the complex conjugate of this, and that's the form where we're going to use it. We find in which we'll use it, we find that x a k bar p bar a of phi bar, then k is I mu x plus mu bar x of phi bar. So this is a relation which we'll use later on, in fact, to relate Kähler gauge transformation to these moment maps. And it tells you how this the anti-holomorphic part of the killing vector. So that's gone now. No, here it is. How this part acts on the potential k. Okay. Okay, that's deriving some of the necessary relations that we'll need later on. But now we have to talk about gauging of this kind of model. And it's clear that we cannot use the kind of minimal prescription or minimal substitution, whatever you want to call it. This relation doesn't work because we don't have the components, we have just k. So then it's back to how you treat super Yang-Mills. Because that's where the technique was developed. And what you do is most easily illustrated on a simple k. So let's look at k of phi bar, which is equal to phi bar. So it's a flat space simple thing. This. But we clearly have isometries here, and we can gauge the isometries. So I should keep track of time, I guess. Yeah, we'll take a break in about a quarter of an hour from now. So now I have to erase all my useful relations here. So we start over here.
So n equals 1 to 5 are basically real, right? They're not narrow.
In n is 1, yes. Yeah. We're not doing, but now we're in the n is 2, yeah. So clearly we have isometries. Which take phi, a very simple phi to the EIX phi. That's an isometry. So phi bar, of course, then x is real. So phi bar phi goes into phi bar e to the minus ix e to the ix phi. So that's invariant. Okay. But now we want to gauge this in superspace. So gauging means that xa, which was constant here, goes to lambda a, which is a super field. And then, of course, to keep the chirality and the conditions on these, and to have phi bar. So if phi transforms with lambda, phi bar will transform with lambda bar, and that means that we will actually have to consider gauging not of this, but of a complexified group. And in particular,
X is just a single index then, or is it?
Oh, this is not the, sorry, where I've used X for 2. This is the X in the manifold. This X is my isometry. And what were you asking?
That X is really a matrix.
Okay, the way I've written it here, it is a matrix. So I'm thinking of that particular case. Quite generally, we will have e to the Lie derivative of along x of phi. So that covers everything. We will use that in case. But it's just easier to discuss it in this form, I thought. So what we have to do is we have to introduce phi tilde, which is e to the is phi bar e to the v, And EV is a real superfield. And we can keep invariance in the local case if V transforms with I lambda minus I lambda bar. So it's sort of bridging the difference between the two transformations. And well, I mean, clearly, if we write, if we replace, no, we introduce V in this fashion, we will have phi tilde phi will go into phi, so this will be phi bar e to the minus I lambda bar e to the I lambda bar minus I lambda, which is plus V, and then e to the I lambda. So this will be invariant. Okay. So that's why this real superfield is needed, and you may wonder, well, how's that related to what we did in the N=1 case, where we had a connection that entered, and the answer is that connection is part of the N=1 components of this superfield V. Okay, so
what happens when these lambdas are matrices? Does that automatically cancel out? I mean, it's leading order it does, the lambdas. But,
yeah, maybe I should have written it as.
Baker does.
Yeah, I know what you're referring to. So maybe a better way of writing it would be E.
You put E to the E in the middle, and then you're.
Yeah, exactly. That's what I wanted. E to E. Oh, okay, yeah.
Right the other way around.
E to the V, E to the minus I lambda. This is the correct way of writing it, and so make sure it works in all cases. Thank you. Anyway, this is the fact that we've now seen what the gauge transformations look like. We can in fact call this introduce this V. So we can write phi tilde is e to the Lie derivative acting on phi bar with I lambda bar, lambda equal to IV. That's going to give us that's going to introduce V. So that's just a convenient way of writing phi tilde that we'll use from now on.
So this transformation of V that you have down there, that's just the leading order part, because then we have the real transformation is what you just wrote.
Yeah, that's what we want. So now, but I just wanted to do a simple, show why it's necessary to modify things and introduce V. So now we know how to gauge. So remember, the problem is that we want to gauge this one. We don't, and we need to do it in a N=2 supersymmetric way, and that is gauging this to read phi tilde. Okay, with this, we have the action is just gauge invariant if K is okay, so that means that K of phi tilde is invariant under lambda transformations. If we didn't have any Kähler gauge transformations in the global case. So this will now work as long as we don't have Kähler gauge transformations that K goes into.
Can I ask a question, please?
Yeah.
Can I think of phi bar ETIV as being a transformation by the complex phi too?
Yeah.
Okay.
Yeah. Exact. That's what it is.
And the result is supposed to be phi tilde, or should it be phi bar?
Phi tilde is when you act with this Lie derivative with parameter IV on phi bar.
Okay.
Yeah. Right. So that's. That's that case. But this, I stress that this is only invariant if the global isometry didn't have a Kähler gauge transformation when it acts on K. Okay, so let me just at least start with what we should do in that case. So if X on K, if this is satisfied, so if this is equal to a Kähler gauge transformation, I'm not sure Kähler gauge transformation is the best nomenclature, but that's stuck. So this is a Kähler gauge transformation. If this is true, then we will have, then we'll get terms like, well, X times nu X plus u bar X, etc. In the this of course, when X is constant, this I've dropped the measure. When X is constant, this is 0. But when this goes into a lambda bar, for example, then this is non-zero, right? So we have to find a way of dealing with this. We don't have a globally invariant, a locally invariant theory when we have Kähler gauge transformations. And I'm thinking maybe we should take a break now, and then I'll tell you how the remedy for this after the break. So, okay, let's continue. So we find that in the case where the global isometries, not global isometries, but in the isometries which haven't been gauged, when they give us a Kähler gauge transformation, then this prescription for gauging the isometry doesn't work, because it leaves this sort of term which isn't going to disappear. So the remedy. So we add to the original K minus zeta bar, where these are chiral, and that's anti-chiral fields. So we have that K, what shall we call it, K tilde, K goes into this, which is this minus zeta bar. Now, of course, these are annihilated, just like the Kähler-Gauge transformation, but the advantage is that we can now prescribe a transformation of zeta and a transformation of zeta bar, which cancels these kind of terms. So that's what we're doing. And what we do is, when we do that, we'll find that our killing vectors have to be modified. So K prime A is K A plus, so remember these are, so it's KAP dP plus, in this case now, eta A d zeta. So K bar prime A is K bar P bar dP bar plus eta bar A d by d zeta bar. So if we do that, then we'll have an invariance, because these two will generate this kind of term, but when the zeta minus zeta bar will cancel that. So we'll have something which is indeed invariant under the ungauged transformation. And we know that this one, we do this substitution for a K which is invariant under the non-gauged ones, then this will be the gauged version, and that will be locally invariant. All right, so what we do is that we let K, which was K of phi bar, will go into K tilde of phi bar minus zeta bar, which in turn we gauge in this, using that prescription. So that goes into now, I don't know, maybe I'll call it hat or something. K hat of phi zeta phi tilde zeta tilde, which is equal to K K tilde, I'm sorry about the notation, I hope you can follow. Which is this. Okay. So this is what we had before, although I didn't call it K tilde, but I should. And these are the new contributions. And now what we'll be focusing on this one to find the final gauged version. And here comes set of formal manipulations which can be done, but which maybe you want to think more about when you get home. So let's look at zeta tilde. We know what it is. It is e to the L prime IV times zeta bar. So by L prime I mean that I've used the primed killing vectors. And this we massage a little bit, say that this is equal to zeta bar plus e to the L prime IV minus 1 over L prime IV times L IV on zeta bar. So you see that that's formally the same thing, because these cancel and you get the minus 1 zeta and so on. And the reason we're doing this is because that will give us a relation to the where are they? Here. The Kähler-Gauge transformation and so on. So this is equal to zeta bar plus this thing e to the LIV minus 1 over LIV acting on, and here we get the nu from down there, and we get we get nu bar V, and there's an I in here. Okay. And I took away the prime without mentioning it, because now, of course, this is only a function of phi bar. It's not a function of zeta anymore. And the primed guys, they have terms that deal with the zetas. So we can now replace L prime by L. Okay. But that means that we can write our K hat as K of phi tilde minus zeta, because we haven't done anything to the zeta, it was only to the bar, zeta bar, but the zeta bar we took out of this expressions. We get this plus I times e to the LIV minus 1 over LIV eta bar, and this is a V. Okay, but then of course, and this term is the one we want. So these are just as before. It's a chiral and an antichiral, and they're killed by the measure, but this remains here. Okay. All right, so now we have one form of the invariant potential, but we still want to massage it a little bit, and that's when we're going to be able to use the relation between nu and mu later on. So we want to expand this phi bar. So we will rewrite that K of phi tilde, and we use the same sort of trick that we did here. We write that as K of phi bar, and then okay, I'll write this as e to the LIV acting on K. Now remember that this Lie derivative only sees the phi bars, and you can convince yourself that this is in fact the same as this, but maybe it's easiest to do that in the phi tilde phi simple k. But this is in fact true. And this is now, I'll rewrite that as k of phi bar plus I'm just using the same trick, LIV minus 1 over LIV on K. And now we're getting to use this kind of relation we had here, which is how a K bar acts on K. Okay, so I'm going to use this relation. Maybe I shouldn't erase it then, so I'll keep going. So this LIV, so I'm now looking at this, LIV on K, by definition is IVA K bar A P bar K comma P bar. Okay, so this is, I'm just rewriting this, only this term, and then the result I'll plug back into that relation. So what is this? Well, this is, according to this thing up here, we have precisely that relation. So we get that this is equal to I times mu V plus nu bar V of phi bar. Okay. So the blackboard has gotten a little messy, so I'll rewrite this relation. So I'll rewrite K hat. Don't know if I should, maybe I'll do it here. So this means that K hat is equal to K of phi bar plus e to the LIV minus 1 over LIV acting on now I times nu V plus mu V plus nu bar V. Okay, so that's from this term. But to this I also have to add this one. And this one, actually, what I haven't done here is you have to remember, I was writing zeta bar, but what enters into the K hat is really minus zeta bar. So I need this one. Is that right? I think so. Okay, so this is so I have to add this term. I've done I've done this K, and I have to add the one from zeta twiddle. So that's minus I times e to the LIV minus 1 over LIV mu bar V. And as I indicated before, then a miracle happens, and this cancels that. So we find the final version of the gauged potential to be this. Oh, this should have an I, right? No? It should be minus here. And this is the final version, almost. But there's one thing you could think about is hermeticity of this thing, and it can be shown that this form of the action, or of the potential, is really Hermitian. Well, this one is clear, but this should be K or phi bar. It's Hermitian, and you can use that to write this in a manifestly Hermitian way, but we're not going to do that. We're just going to look at how you. So this is the gauged version. Where is the potential? It's here. So extremizing this to find the new potential, what we have to do is that we have to vary this mess here and find what it tells us. That is intricate, but we can write away. We can write down the result of that at least. So d delta v implies that e to the LIV mu a is 0. And that, first of all, it's not easy to see that that is what you get from the variation, but it is. And the other thing is, it's not very easy to see what it means. But for V, because this is what we have to solve for V now and plug back in, right, to get the extremized potential. Okay, and if you look in the papers, we have a slightly different version of this, which is e to the y mu a is 0, where y is a half vj, isn't it? Yeah. And the derivative. K, where K is the full Killing vector, both the holomorphic and the anti-holomorphic part. So this is, when we write it like that, that's then hermeticity is manifest. But that is not something we're going to use really. What we are going to use what we are going to do is we're going to look at an example, and the example will look trivial as compared to this, but you can come up with more complicated examples if you want to. But just to see the working of the whole thing, this is an example that I like. So what we have is we start from a potential K of phi bar, which is equal to the thing that I've been using before. Just sum of two quadratic terms. Okay, and this just gives you the metric on if you look at the metric that you get from this one using the relation to the metric that we used to have here. So you see that it's going to be just constants. So this gives us the metric, one metric on C2. So that's the sort of starting point we have in these quotient constructions. Start from something which is easy, which is simple, and which gives you has isometries. And then what we do now is we integrate out. We first look at the isometries, which I write like this. So it's this and the bar and you have a bar for the other one. So you see that that's going to cancel, and then okay, and then it turns out. So I leave as an exercise to show that the moment map is really psi times k minus a constant c. There's a story behind being allowed to add that constant, but this is what the moment map looks like. And then if you plug that, if you use that and write down this form, which looks messy here, it becomes very simple. It becomes k of phi twiddle is phi bar p phi p e to the v minus cv. Okay. So then you eliminate. You're supposed to. This is the gauge. This is the fully gauge invariant, locally gauge invariant potential, and then you integrate out v, and you find that v is minus the logarithm of phi bar p over phi times phi p over c. And then you want to plug that in back in. I don't know. I'll go over here. So the next step, if you remember, we found the v that extremizes that k, and we plug that back in, and you find that k goes into a c times logarithm of 1 plus phi bar phi plus f of capital phi plus f bar of phi bar. And I have to tell you what this is just a Kähler gauge transformation. So it doesn't change the geometry. But these phi's are phi is just simply this quotient. Okay. So now you found this potential, and then you can find the metric phi bar which is d to d phi bar. Okay, and that is in fact if you work it out, you find a Fubini study. Metric. on CP1. So this is the sort of thing you can do with these quotients, or reductions, as some people say, which is you can start from a very simple geometry with the right symmetries, and then you go through the procedure and you find a new sigma model, or you find a new geometry, and in this case it led us from flat space to CP1. Okay, so right. But after all, we were really interested in starting from a simple hyperkähler and generate a new hyperkähler. And having done all this, I'll just sketch the final story, because all the intricacies are already in here, in this construction. This construction, by the way, is the Marsden-Weinstein symplectic reduction. So symplectic in this case is the Kähler form. So we've recovered that using superspace and sigma models, and for a hyperkähler, we know that we have to start from a Kähler model which has some additional properties. So we start from a K of phi and phi bar, but we also need to gauge it, and the key things in gauging was remember that we introduced in NS1 we had a V, in NS2 that has to have partners, so we get that goes into V, S, and S bar. So it's a vector field. We call it a vector field when it's just a real superfield, and chiral and anti-chiral fields. So this is because we cannot write it in NS2 superspace. We write it in okay, so when I say NS2 here, I'm thinking in terms of it's 4 dimensions, I think. So I should do this, and I should call this 4 in 3 dimensions. So we cannot write a manifestly NS4 sigma model. We have to have a NS2 sigma model, which is this one, and have some extra conditions. And what are these extra conditions? Well, they're the fact that there's not just one complex structure. There are 3 extra, and they satisfy the algebra of the quaternions and so on. But the construction then also involves the moment map, or killing potential. I backtrack and I've erased that, but there was a relation which showed you that mu is really a potential for the killing vectors. I can write it again, but this now gets also into a multiplet, and the multiplet contains 2 more moment maps, mu plus and minus, and the action, the gauged action, which starts out from this. So So we have, I think I called it K hat. Let me be explicit. K of phi tilde plus, oh, that's not very explicit. It is the usual K hat of phi bar and V that we constructed over here. So that's this K hat. So that's one part of it, but then that just deals with this moment map. There is also plus these guys. Let me write it. D squared mu plus S plus a half D bar squared mu plus mu minus S bar. So these are the extra terms you have to add to make the action invariant under for supersymmetries. And here the mu S plus is S A mu A plus and mu S bar minus SS bar A mu A minus. So very similar. And what we have to do to find the quotient now is not just integrate out V, but we also have to integrate out the scalar fields S and S bar. I say integrate out, but don't be misled. I mean, what we're doing is we're extremizing, finding a solution that extremizes the action and plugging that back in. That's the full story. And then we have to plug back. And then we have the quotient that gives us the Hyperkähler. Okay, so that's in words what we're supposed to do. I should also make some comments about this. One of them is that a key thing to all this is preserving supersymmetry in the reduction when we do the quotient, and that is in fact the case. I don't have time or space to go through that, but here global issues and supersymmetry, etc., are all under control. And this is a global construction, in fact. I've not mentioned the isometries here, because of course this should have isometries for this construction to be possible. And whereas the isometries were holomorphic for the symplectic quotient, here they have to be triholomorphic. Isometries. Which means that they're holomorphic with respect to all the JIs, all the three JIs. Other things that I haven't even touched is that, you know, for this moment map or killing potential to be well defined, you have to check a number of consistency conditions, and typically that is that introduces a number of different conditions. I mean, you remember that there's an algebra for this K, and you have to check that these the killing vectors, that they're equivariant, which is a condition involving the Lie bracket and so on. And there are several other conditions that I haven't talked about, but I've covered, I think, the main ideas in these couple of papers and other discussions. So thank you for your attention. That's where I run out of steam.